Yep. So, your assignment breaks apart these problems into a group that only has one variable to replace and a group that has two variables to replace, but there's not a dime's worth of difference between them. If there's two variables, you just look at their values and put them in and calculate. My only point about this was, in real life, when we're going to do a problem or solve something, you have to decide what really matters and what doesn't, what really counts and what doesn't, what can really be used and what doesn't, because you have data that comes in by the millions of stacks on your desk and on your computer and all like that. And you can have a bunch of information, here's what I'm saying, but probably most of the information is not important, but it's up to you to decide sometime what really matters and what doesn't. Okay, here, especially in word problems, we don't do many word problems, but if we did, I'd give you extra information, so you'd have to decide if it really is necessary or not.
-3 plus 2.
Very good, sir. But for one or two people that might prefer to have it like that first, I'll put it. Right? Same thing here, bunch of negatives. But I wouldn't blame you for going ahead and changing it to plus, saves writing all that mess. Am I doing it right?
Yep. Yes, sir.
Okay. That's evaluating. Here. Back to one variable again. Oh, but unfortunately it's on the bottom. Wouldn't you know it? Story of my life. Might as well do what we can easily first. Want to combine those two? Order doesn't matter. But we can't leave it like that. While I'm thinking about it, if you had a case like that, if something like that came up as the answer, not this, but pretend like that came up, you could write that as 5 2/3, and I would give you credit. But you better be careful with something like that here. For one thing, we've got a minus sign. Another thing, it's an improper fraction. So the best thing to do here, well, in real life, what you would want to do is to change 9/2 to 4.5, 4.5, and then 4.5 minus 14 is minus 9.5. But that's not what you're expected to do. You're expected to take these two and make a single fraction out of it. Combine these fractions. Right? Which means you've got to get an LCD, you've got to get a common denominator, combine them over a common denominator. So we'll go back to the basics about fractions real quickly. When you're combining two fractions, by that I mean adding or subtracting, you can never add denominators. And the only time you can add numerators is when the denominators are the same. So the first step is to get the denominators the same. When the denominators are the same, you combine them, keep the denominator, and add the numerators. So this is really 14/1, isn't it?
Yep.
So we need to change that denominator 1 to 2. So we have a common denominator. What does it take to change 1 to 2? Multiply by 2. See, I'm trying to get the denominators the same. It's the only way we're going to combine the two fractions. So you have to multiply this 1 by 2 to make it equal to this one. But on any fraction, if you change the denominator, you've got to change the numerator by exactly the same amount. And isn't that okay? Because we're really multiplying by 1. We're multiplying by 2/2, which is equivalent to 1. That was the identity property of multiplication, if you recall. So 9 halves minus 28 halves. Didn't we just do the opposite of reducing? Because if I gave you 28 halves, you should reduce that to 14. In this case, divide. 28 divided by 2 and get 14. I just did the opposite. I changed the 14 to 28 halves, which makes it worse. That's the only time I know when you deliberately make a fraction worse in order to add, to get a common denominator. I can't think of any other time. So now that we've got a common denominator, you keep it, make one fraction out of it, you combine the numerators. 9 minus 28 is negative 19 halves. Now that's the final answer as a fraction. But if you were to divide 2 into 19, you'd get 9.5. So most of the work there is after you evaluate just getting the fraction. All right, did you feel pretty confident on that? So all we covered was when you have an algebraic expression, and so far we haven't identified what the expressions are, what the names of them, the types of them, any of that. It's just some expression with numbers, operations, and variables in it, and you're asked to evaluate. Somebody will tell you what the values of the variables are. You put them in, use PEMDAS to evaluate. Gary Johnson, NBC News, New York. Okay. Now, I told you there are two common instructions for expressions. The first was evaluate. The second is simplify. Now, there are other instructions you'll have, such as graph and factor, but the most common instructions are evaluate and simplify. So let's talk about simplifying now. In order to do that, we're going to first define the word term. And I think you know what it is, but I'll define it. It's on my paper. A term is the product of a number, which is called the coefficient or numerical coefficient, and variables to exponents. So normally, usually you'll have a number followed by some variables to exponents. Is it possible not to have any variables? Yes. A number by itself is a term. I'm trying to anticipate your questions. So a number by itself is a term, and that's called a constant term. So let's make sure we understand what a term is. Let me give you some examples. Is that a term? Is that a term? Is that a term? Is that a term? And my answer to all four of those questions, yes, all four of those are terms. Now, if there are terms, which they are, I should be able to ask you, well, what's the coefficient of the term, and what's the variable part of the term? Now, the variable part is what comes after the coefficient. Everything after the coefficient is the variable part. Did you leave an extra space to write this in? So really, the term consists of the coefficient and the variable part. So tell me on the first term here, what's the coefficient?
The 4.
What's the variable part?
X.
X squared y cubed, yeah? X, okay, 4, x squared y cubed. What's this? How about this? What's the coefficient?
X.
X. I don't see a one. Oh, you mean the one that's under here?
Oh.
You know what? There are ones all over the place and we never show them. There is a default, you guys are familiar with computers better than I am, right? Aren't there sometimes default things, if you don't specify what it is, it just automatically assumes something? In fact, sometimes on settings, you have to tell them what you want the default to be or you'll get messed up sometime. I put this here because you know what? Everything has a denominator, whether it's shown or not, because the denominator is 1. Everything has an exponent, whether it's shown or not. X is 1, Y is 1, Z is 1, right there. This 4 is 1. Everything has an exponent, and if it's not shown, it's 1. Now we go beyond that now, and I'm saying that every term has a coefficient in front. And if it's not shown, it's 1. But we don't show a lot of those ones, we just know it's there. So the correct answer is yes, 1 is the coefficient here. And the variable part is x, y, z. How about this? Is this a term? Yes, it is.
Yes.
What is, it is a constant term. A constant term. What is the coefficient? You're afraid to answer.
The number itself.
It's the number itself.
Okay.
It is the number itself. It's negative 1/3. So there's always a coefficient. There may not be a variable part, but there's always a coefficient. So if there's no variable, this is the coefficient, negative 138, no variable part. And this one, what's the coefficient? 10, variable part, x to the 14th. So now you're wondering, well, what isn't a term? I don't understand. Everything looks like a term. Well, there's one main exception I know of, and that comes from the definition here where I say a product. Product means multiply. If you had variables on the bottom instead of on the top, that's technically not a term. That's division, and that's not a term. Now, there are some aspects of terms that this would still qualify, but not overall. So this is not considered a term. And so I know what you're thinking. You're trying to learn a pattern here. So you think, okay, I can't have anything on the bottom. Well, don't think that. If we turn this upside down, write it that way, believe it or not, that's a term. You say, why? The 4's on the bottom. Yeah, but you know what? You can write this as 1/4 x squared y. Those are equivalent. So the coefficient is 1/4. See, we don't have to have an integer coefficient necessarily. Any number in front would be a coefficient. So if you've got a number on the bottom, you can bring it out front like this and regard it as part of the coefficient. So this variable part's x squared y. This is the only one on the board that's not a term right there. Now, the variable part is very important because we're going to be talking about like terms, and like terms have to have exactly the same variable part. Okay, coming up in just a minute. In fact, how about right now? The definition of like terms. Like terms have the same variable part. EART, same variable part. So let's see what we have some like terms here. What I'm trying to show here is that we have 1, 2, 3, 4, 5, 6 terms I've listed on the board. Do we have some like terms?
Yes.
Oh, I see what you mean. The minus 4x cubed and the minus 4x and the minus 4, they're like, right? All the 4's are the same in all three of those. The minus 4x cubed, the minus 4x, the minus 4. Yeah, those are like terms. No? Oh, so you're saying it's not the coefficients that matter?
No,
Oh.
it's
It's the variable part that
Yeah.
matters. Okay. Well then, you know what? The first step in simplifying a bunch of terms is to look at the variable parts and see if they're the same. So you say, okay, this is an x cubed term. I call this an x cubed term. It's got a coefficient -4. It needs to simplify or be combined with another x cubed term. And so you look down the line, nope, not that one, nope, not that one, but this one. These two need to be combined. And I'm going to write on the board in a moment how to combine them. Now this x squared, we can only combine with another x squared. I don't see one. This is an x term. We can combine with that one. And you need to always combine like terms if you can. And here's how you do it. Combine like terms, which means they have the same variable part. Yeah? Combine like terms by keeping the variable part. Don't you change it at all. Keep the variable part, but combine the coefficients. And since some may be positive and some negative, right? Because I taught you to keep the sign with the number. Some may be positive, some negative. So when you combine them by the rules of sign to numbers. In other words, same signs add, keep the sign. Opposite signs subtract, keep the sign of the larger number. Now, let's go back to this problem. Let's go ahead and put the plus right there since we're assuming that's a plus 9. Let's put the plus there. Let's put the plus here. Now, what we have here now is a sum of 6 terms, right? And what's the coefficient of the 4th term? 9? What's the coefficient of the last term?
-4.
What's the coefficient of the first term?
Negative.
Okay. Now we've got 6 terms here that are kind of being added together. The definition of terms being added together is called a polynomial, which we'll be referring to in the rest of the course. A sum of terms is called a polynomial. So if you're given a polynomial like this, you can be asked to simplify it. This is the first kind of expression in this course we'll learn where you're asked to simplify the expression. Okay? How you simplify a polynomial is you combine like terms. Really, you shouldn't even have to be told to do that. If you're given a polynomial, you should automatically look and see if there are like terms and combine them. Now, we just finished saying that this minus 4x cubed and the 9x cubed are like terms. Therefore, we will combine them by keeping the variable part, combining the coefficients. Aren't they both x cubed terms?
Yep.
Keep the x cubed. Don't change the x to the 6th or anything like that. X cubed. But we combine the minus 4 plus 9. What's minus 4 plus 9? Positive 5. There's the result of combining those. Everybody agree? And if it's a long list of terms, you might as well cross it out when you use them up so you're not looking back at it again. Next one's an x squared, I see. Well, is there any other term to combine it with?
No.
No, there's not, so you just rewrite it. Yes, we do. There it is. Well, cross it out. Next one's an x term. And we decided?
Yes.
We'll combine it with that one.
Negative X.
Keep the x, yep, and combine the numbers and we get -1, which we don't have to write the 1. You can just put minus x. Realizing it means -1. That's what it is. And we used them all up except the -4. That's the answer. That's simplified. If the instructions had said this very problem, if the instructions had said simplify, that's what you would do, combine like terms. Now I'm about to say something that I'll be saying probably every class. The purpose, I've already said this, I'll say it again. The purpose of an expression like this, any expression, is that it's waiting for somebody to tell you what x is so that you can replace x with the number and evaluate it. That's why it's there. But don't ever evaluate an expression until you first simplify it. Simplify always precedes evaluate. See, if somebody gave you this and said, I want you to evaluate that for x equal -2, guy, you should say to him, go find yourself a cup of coffee or whatever you like. Because I do not want to put your silly -2 for x or whatever you want, and I know it'll be negative just to challenge me. I'm not going to put that number in here because I'll have more chance of a mistake if I do that, and it'll take me longer. I would rather simplify it first. So you simplify it by combining like terms and get this. Then you call the guy back and say, now what was it you wanted me to evaluate it for? And he would say -2. I want x to be -2, which of course is my favorite number. So you put the -2 in there. Since I started it, we might as well finish it. All my idea. See? But as much work as this is, it's still easier than that would have been. I think that's -6. So if you put -6 in the original, you would still, if you had put -2 in the original, you would still get -6. It would just take more work. There are plenty of cases where it even turns out simpler than that. It's always better to simplify first. In fact, that's what the word simplify means. Make it easier to evaluate. It's only there to evaluate. That's its purpose in life. But make it simpler first before you evaluate. Not only is it easier this time, but maybe tomorrow he'll have another value for x, and the next day another value for x. So every day that he wants you to evaluate it, you're much better off using this than that. And besides, you might start keeping a catalog of this, because a month from now he might ask you to do it for -2 again, and you say, well, I kept that one. Computers do that. They keep a catalog sometimes of commonly used values so they don't have to recalculate it. Alrighty, so let me just do another one real quick. I only stop when I run out of space. So, there you go. Is that a polynomial? How many terms are there?
A lot.
Yeah. I like 7. You know, it's easy to calculate the terms because every time you get to a plus or minus sign, that ends the term and starts another one. Because the definition of a term is the product of stuff. And so when it stops being a product, that's when adding and subtracting stops the product, starts another one, starts another one. So if there are 6 plus and minus signs, there must be 7 terms. if the first one's positive. Anyway, yeah, that's right. So I might ask you now two steps. First step, simplify. Second step, evaluate. And let's just make it simple for a change. X equal -1, Y equal -1. Now actually, you could do that in the original pretty easy. But need to simplify first. You know, when I make up a problem, I have no idea what the answer is going to be. I just go by faith. That I can get there because I've done it every year, so I can still do it, and it works. Now, did you work on it? Did you get this? Did I do it right? Is it 2x squared y?
Yes.
Oh, here, I'm blocking this one. So this one combines with that one. There it is. This minus x squared combines with that one. There it is. This 4 and this 3 combine. There it is. Now, what you could do, if you really wanted to, in a long list like that, you got time, you can reorder all the terms and put all the like terms together. Rewrite them to where they're together, and then it makes more sense that you can just deal with each group separately. But, if you can do it this way, that's even better. You don't have to rewrite it. So I think that's the answer. And if anybody wonders if the order of these terms matters, can I regroup them? The order does not matter. Order does not matter. So now it's time to evaluate. And if everything's -1, there's actually an easier way than having to put it in here and calculate it, but we will. -4. So, to make a long story short, if you've got a polynomial, okay, sum of terms, simplify by combining like terms, then evaluate. Oh, but there can be parentheses in it to where you have to use the distributive law, distributive property. They used to call it the distributive law. But I guess it sounded too much like politics. Such as this. Let's pay attention to this because you need to be real confident that you can do something like this. I stopped too soon, but I was getting tired. Now the instructions here would be simplify, simplify. Now, what you really should do in the middle of a final exam is to look first and see if there are X's in it, but there's a whole bunch of X's, so it solves that question right away, because you know if there were no X's in it, you'd use PEMDAS. Okay, since there are X's in it, that's out of the question. However, a simplified answer, ladies and gentlemen, will never have parentheses in it. That's part of simplifying. You got to get rid of parentheses. Now, if you can't use PEMDAS to get rid of parentheses, you have no choice but to distribute. Distributing gets rid of parentheses. The distributive principle. Remember we had on the board. Is that part of the Veteran Day? Remember that whatever is in front of parentheses, and something is either being added or subtracted inside the parentheses, that what's outside is distributed to everything inside. Multiplied. Distributed means multiply. So this 2 is distributed. This minus 3 is distributed. Now this is all part of 1.2 for your homework. And it's not an equation, is it? We haven't gotten equations yet. There's no equal sign in any of this. All we're being asked to do is to make it simpler, which effectively means combine like terms. That's what it means. But we can't do that as long as there's parentheses. These parentheses are hiding the terms. We have to get rid of the parentheses so the terms come out in the open. All right. This 2 has got to multiply both of these. Just do one thing at a time. 2 times 3x
6x.
is 6x. Now see, there it is, 2 times 3x. We're really multiplying 3 things. 2 times 3 times x. But remember, the associative law of multiplication says you can choose any 2 that you want to multiply first, and you might as well choose the 2 that you do know how to multiply. I can't multiply by x till somebody tells me what it is, but I can multiply the 2 times 3 and get 6. That's what you do. 2 times 3x is 6x. Then 2 times the minus 4.
Minus 8.
Minus 8. Now, we've gotten rid of the parentheses there. Okay, we'll do the same thing over here. Negative 3 times x squared.
Negative 3x squared.
Negative 3x squared. Negative 3 times negative 5x
15 plus 15x.
plus 15x. Okay, we got rid of those parentheses. And we're getting some like terms here. Minus 2x squared
Minus 5x.
minus 5x. Now sometimes it's tempting to combine unlike terms. Stop yourself from giving in to that temptation. Only combine like terms, same variable part. And here's something else we need to get used to. Most of the time, it's a big help if you've only got one variable. I don't see a y in here anyway. So if you've only got one variable, it's better to start with the term at the highest exponent first. This is called standard order. Yeah? Polynomials should be in standard order. Everybody expects it. And later on, it's essential really to factor them, things we need to do with them. So it's better to write them in standard order. So if they're not in the highest exponent first, I think we ought to start with the highest exponent and go down to the constant term. That's standard order. Then we all have the same answer. Oh, math teachers love everybody with exactly the same answer. Even though we already learned an hour or so ago that order doesn't matter when you're adding terms. I agree with you. We get the same answer no matter what the order is. But for standardization, it's better to start off with the highest exponent. So we glance down and see, okay, the highest exponent is 2. So let's combine those first.
Negative 5x squared.
Now comes x.
Plus 16x.
We have 6x plus 15x minus 5x. You can combine those in any order you want. In fact, I just did it in my head 3 different ways and got the same answer, except I forget what it was. Oh, 16x.
Minus 8.
Minus 8. That's the answer. We've simplified that polynomial into that. This is called a trinomial. It's got 3 terms. It's in standard order, starting with the highest exponent. It has degree 2. The degree is the highest exponent. That actually characterizes this. If we were to graph this, which we will do something like this in Module 8, you'll see that the first term characterizes the whole graph, the whole characteristics of that. In fact, see, the smallest thing is this little exponent 2, but it's the most important thing. It's the fact that it has an x squared term. This is called a quadratic expression. An x squared in it makes it quadratic. No, you remember these things. When you set this equal to 0, it becomes a quadratic equation. And we solve quadratic equations using the quadratic formula. And we'll get to that in Module 8. So any question about this? Oh, we can evaluate it, especially if you're trying to kill time. Evaluate. For x equal -3. You know it'd be negative. Please evaluate that. I want you to be able to do it quick. Some big negative number, huh? To me, big means over 30. I used to think old age meant over 30. 101? Okay? All right, summarize this. Because this will be the hardest kind of problem you'll have in 1.2, which somebody finally got across to me is due Saturday, is you will have expressions like this that you are asked to simplify. And if it's got parentheses, distribute. Then combine like terms. Distribute and combine like terms. That's what simplifying polynomials means. Now that was actually, I know something else I wanted to say. Are those like terms?
No.
What do you think?
No.
What would you say? You're afraid when I ask a trick question because you think, well, a good case could be made that they are, and a good case could be made that they're not. It depends on what side of the fence I'm on. Because I said like terms have to have exactly the same variable part. However, there's always an asterisk there. We decided that the the commutative property and the associative property says that we can write these x, y's, and z's in any order we want, and it's equivalent. It's equivalent. So if it's equivalent, then it's the same. I mean, if you can combine terms, are you going to let the fact that they happen to be written in another order going to stop you? You're trying to make it as simple as you can. And if x, y, z is the same as y, x, z, why keep them separate? Therefore, from now on, always write variables in alphabetical order, anytime. And then you'll automatically recognize them as like terms. You might not recognize them as like. These are like. These are all three like. But you might not recognize it if they're not in alphabetical order. The answer to that is x, y, z. Right? 1 x, y, z. I'm going to start module 2. Sorry. I think, you know, this is simple enough. Everybody ought to make 100 real easy on 1.1 and 1.2. Do that, do the discussion. That discussion 1 again only has to do with how you're going to study math, what resources you're going to use to study math. If you want to say my teacher's so good I don't need anything else, that's quite all right with me. 20 points for sure. Okay, module 2 deals with solving equations. And not just any kind of equation, but a linear equation. You've got to get ahead. You've got to get ahead, so I've got to keep going. Solving linear equations. Now remember, there's a big difference between an equation and an expression. An equation has an equal sign. In fact, the real definition of an equation is an expression on one side of the equal sign equals another expression on the other side of the equal sign. Of course, it could be as simple as a single number, or it could be a bunch of x's to different exponents, things like that. But in any case, expression on the left, expression on the right. Now say it just has an x in it. We're not going to be talking about equations with both x and y in it right now. So we're just going to have x in it. Since we've already gone through the fact that expressions are meant to be evaluated, that's what they're for. Say I ask you to evaluate the expression on the left for my favorite number, -2. And I ask you to evaluate the expression on the right also for my favorite number. Now these are two different expressions. They're not the same. I'm telling you. Two totally different expressions. We've got them equal. And I'm asking you to evaluate the left one and evaluate the right one for the same number. Now, equal means they've got to be the same. That's what equal stands for. Equal means that once you evaluate the left side with -2 and you evaluate the right side using PEMDAS, -2, you end up with exactly the same number. Now, what are the chances, do you think, that if we just pick a number out of the air for some two expressions, I'm not even telling you what they are, but could make them up, and I'm asking you to evaluate both of them for -2, what are the chances they're going to turn out to be equal? Very, very small probability. I mean, I could just give you any number and ask you to evaluate, they're going to turn out to be the same. They're two different expressions. That's why with an equation, you just can't let x be anything. You can't let x be -2, and I think I'll change it to 10 or something else, and it won't work. You've got to decide. You've got to figure out what value of x makes it so that when you evaluate the left, and you evaluate the right, you end up with the same number. And there's only one. It's been proven there's only one. Now, later on in the course, we'll be talking about equations where there are two. But the equations we're talking about right now will not have x squared in them. That's why it's called a linear equation. A linear equation, no x squared in it. That's what it means. It's just x. Just x and numbers. X terms and numbers. That's all. So if all it's got in it is x terms and numbers, there will only be one solution, and you have to decide what it is. That's totally different than evaluate. That's solve. Okay, so we've got to come up with some procedures to solve equations. Now, there are a couple of basic fundamental principles that we're going to follow to do this. The first principle is we're going to create a sequence of equivalent equations. By the way, I have a handout on Module 2 I'll bring next time, okay? We're going to create a sequence of equivalent equations. So we're going to start out with an original equation that you're given to solve. And we're trying to figure out what value of x makes that true. Well, in order to do that, we create a new equation, which is different from the original, but simpler. And from that, we create another equation that's still different from the original, but simpler. And eventually, when we keep doing that over and over again, the very last line will be x equals some number. That's still an equation, but all that's on the left side is x now. And all that's on the right side is a number. And what that means is, that's the solution. That's the answer. X equals that number. So that if we were to take that number and put it back in the original and evaluate the left and right, it would turn out to be the same. Okay, that's the procedure. We're going to form a sequence of equivalent equations. Well, what is the procedure we go about to do that? How do we do that? Well, step 2. Every time we write a new equation, we do the opposite operation of what we see. The opposite operation of what we see. See, solving means to back into the answer. Figure out what x must be in order for this to be true. And we do that by doing the opposite operation of what we see. I'll give you an example in a minute. And then finally, the third principle is whatever we do in creating these new equations, sequence of equations, we must do the same thing to both sides of the equation. Let's do the same thing to both sides. After all, an equation is like a pair of scales. It has two sides, and the equal sign means it's balanced. And it has to be kept balanced. Every line we have a new equation, new equation, new equation. Must maintain balance. And the only way to maintain balance is if you make a change on one side, which will be a change of doing the opposite operation of what you see, you must do the same thing on the other side. Slowly, x gets by itself in doing this process. What does it take to get x by itself? So we've got 3 steps, and we're going to follow those 3 steps in every equation we solve, every linear equation we solve. Simple example to begin with. X plus 3 equals 10. The instruction is solved. What value of x makes that true? Well, this is so simple, you get the answer in your head right away. But what you're not aware of is how you're doing that in your head. I mean, I'm sure you see right away, oh, x must be 23, right? I'm sorry, or x must be 7. X must be 7. Well, why did you say that? Because you're backing into what x must be. In order for x plus 3 to be 10, it must be that x is 7. Well, we can get that without having to think too hard about it, because when the problems get more difficult, you're not going to be able to see it right away, I can tell you that. We need a definite method to get there. But what we would do in this case, we say, okay, there's X right there. I need to figure out what it is. Well, what I'm going to do is I'm going to make a sequence of equivalent equations, which is only going to take one in this case. I'm going to do the opposite operation of what I see, and I'm going to do it on both sides. Now, what's keeping X from being by itself? Because that's what I'm trying to get at right here. The plus 3. The 3 is being added. I need to do the opposite of what I see. That's why when we covered opposite operations last time, I told you we need opposite operations in order to solve equations. That's the only way. So we say, okay, if I'm adding 3 in the original equation, I need to do the opposite. And I need to do it on both sides. And the neat thing is, of course, the plus 3 and the minus 3 go away. What was that called? Oh, the inverse operation of, inverse property of addition, wasn't it? Remember that from the list. So, yes, that goes away, and we're only left with X on the left side. That's what we want. On the right side is where the work is. 10 minus 3 is 7. Now, it's just like reducing a fraction. If it's this simple, you don't go through all that and write it down, you can see it. But also, when things get more complicated, we have no choice but to actually write everything down. And I can see the time is up. I can also hear the rumble.